Let's talk about exam one. I guess this is where I get to say, welcome to organic chemistry. Hi. So, the high grade was a 97, which tells me I taught the stuff. The low grade was a 17, which tells me someone mailed it in. The average was a 66, which is disappointing. Um, the last 3 years, I think the average on the first exam was an 86, an 84, and a 76. Um, yeah, this is the easiest test you're ever going to take in this class. This is as easy as it's ever going to get. So, starting with a 66 ain't great. Last semester, I think it went 86 for the first exam, 66, and 66 for the next two exams. So, we now live in a world where you guys are starting with a 66. There were 6 A's, 12 B's, 20 C's, 14 D's. All those numbers look reasonable. And then 27 F's. Like, what happened, man? I don't get it. Like, it definitely wasn't that hard. Was it long? Yes. In retrospect, maybe I could have given you 10 more minutes, but I don't think 10 minutes is 10 points on the average. I just don't believe that that's what separated like a 66 from a 76 on the average is 10 more minutes. I think part of it may have been that you heard open notes, open book, and that translated into I don't need to prepare at all. Even though the old man sent an email that said, if you do not, this test is long, you won't be able to look up every answer. You have to know this stuff beforehand. I feel like a lot of people were like, old man's making it up. It's not real, right? So it's real, right? Like the next exam is going to be structurally similar, but just more difficult content wise, right? We're gonna go over naming enantiomers today, which for me to ask that just requires me to ask you more naming questions again. So if you couldn't name this time, you better get your life sorted out because you got to have to name every exam that we do. And there's going to be all the reactions that you have to know. So there's a lot more material. Um, yeah, I don't think anyone has 100% played themselves out of passing the class. I don't know if anyone is 100% dead to pass the class. There are people that are in better situations than others, but there are still 400 points left in the semester. In theory, if you got 100 on everything, even if you had a 17, you would get a B. Right? So mathematically, everyone is still live for most grades that you would want. Right? If you got an average grade and then killed it on the next like 3 exams or 2 exams in the final and did really well on the homework and attendance stuff, you could get an A still. Like that's not dead. Now, in a normal semester, the drop date has historically been right after the second exam. That is not the case this semester. The drop date is October 9th, which is in like 3 weeks, 2 weeks, something. So this is the only data point you have for this class, right? So you have to like look deep inside yourself and say, am I going to do better? Right? Am I going to actually like prepare for this test, for these tests, as if I was in a room in person with someone proctoring it where I had no outside assistance in any way, shape, or form? Because that's how I'm going to make all of these exams. And I'm going to kind of hold to that by making it so you have to do them relatively quickly. I don't think there were that much in terms of like naming. I think there was roughly the same amount of naming problems as there were on previous exams. Like if you just look and count, there's pretty close. You didn't have to draw anything. I think the Newman projection problems were easier, right? But they were the same things that you would see in class. Here's a structure, draw a Newman projection. And you just had to pick the one that was right. So, like, if you're gonna put in that work and prepare for the exams as if you were taking it in fall 2019, where like you just come into a room and I'd hand you blank paper and you would fill stuff out, then awesome. If you're not willing to do that, I don't know what to tell you. So like you just need to like, take this more seriously, I guess. I know it is difficult when half the time you're sitting on your bed taking the class or you're taking the exam at like your kitchen table, but these are the times we live in. So just make sure that going forward that we're doing all the right stuff. Aside, I had someone try to lie to me that their computer crashed during the exam to get another go at taking the test. I feel like I'm a reasonable human being, but if I feel like I'm being lied to or manipulated, I will like do so much stuff to ruin you. I spent yesterday going through Moodle trying to figure out how long they actually were in the exam for. I tracked down the people who run Moodle on Coastal who went through the logs and tracked all their activity during the exam so I could see that they were in the exam the entire time. I did a whole bunch of stuff and then sent this detailed email. Don't try to screw me. Like, this semester sucks bad enough as it is. Like, let's all just be decent people. Right? If I feel like you're trying to like manipulate me or lie to me, I will like call various people on campus and be like, I need to know this information and I will build a case against you. Did I like turn this person into like whatever? No, because I'm not a monster. But don't screw with me. I don't want to have to deal with that. So let's do our best to be reasonable human beings because that would make just everyone's life easier. Also, before anyone goes like, average is 66, he just doesn't care. He doesn't care if we learn. He's awful. I stayed up till midnight on Monday for two reasons. One, feed baby. Two, I watched every person log in to the exam and I watched and waited to see what their score was. Because I was like, oh man, the average isn't great. I hope people start doing better. I watched every person go in. I was like, oh, there are 4 people taking it right now. Oh, there's 5 people left. Okay, let me make sure they all get in. I watched everyone take the exam and like watch what their score was because I was worried that the average was low. And I was trying to figure out what was going on. So, like, I was like, oh man, I really wish this was better. I think that, like, I think that I wasn't particularly tricky. I think maybe, like I said, I could maybe give you slightly more time. I don't think it'll make that big of a difference going forward, but I could give you a little bit more time. And maybe the matching problem should have been 2 things of 4 instead of 1 thing of 8, right? But again, I don't think that's like 20 points on the average or 15 points on the average. Like, I don't think that's that big of a difference, right? Like, I feel like, I hope, I'm doing a reasonable job of organizing the class and presenting the material in a way that is organized and understandable, right? Cool. Then it's your job to meet me halfway and learn some shit, right? So like I did not set out to make the exam hard. I wasn't like, oh, excellent, let's get him. No, that was not my intention at all. I actually was like, I hope the average isn't like an 85 because then it'll look like really super duper easy or 90 or something. Like I was like, good like 80 would be fine, whatever, right? When it was 70 early on in the day, I was like, this is okay. It's a C. Nothing screwed here. We're fine. Then when it started going lower, I was like, oh God, right? So like, I think I'm doing my part, right? I know it's not ideal how we're doing this, but I hope I'm doing a decent job, like presenting this stuff in person and online, all that jazz. So like, but you got to meet me halfway. Like, you can't just think like, oh, this is going to be easy because I get to take the exams at home or whatever, because clearly it was not. So this is the world we live in now. This is the average for the first exam. That's not changing, right? You guys just have to do better. There we go. Angry old man out. All right. With that, these two molecules are enantiomers, right? You can see that they are mirror images of one another. I can rotate this so the green part and the black part match up, but then the red and the white don't match, right? So they don't superimpose that way. Also, I can do it where I leave the red and the white, where the white's forward and the red's back, and those can kind of line up. But then the green and the green balls don't line up. Right, so I can kind of get some stuff to match, but not all of it. So these are non-superimposable mirror images of each other. Back to screen share. All right, share. Okay. Alive humans that aren't black boxes. You see that these are mirror images of each other, right? I can turn this, I can line up the green part and the little black stick, but then the red and the white don't line up, right? So they're not superimposable that way. I can kind of leave the white and the red so they line up, but then the rest of the molecule doesn't line up right? So they're not superimposable that way. So these two molecules are enantiomers of each other. So this is the exact same thing that's happening with carbons when we draw the carbons, right? These are your wedge groups. The white things are your dash groups. The black thing that I'm holding and the green are the in-plane groups, right? So this is exactly like a carbon, except for the carbons are much, much smaller. But it's the same concept. All right, so let's talk a little bit more about enantiomers here. Oh, one more thing about Angry Old Man. I want all of you to pass. All of you. But what I want more than for you to pass is for you to know some stuff. Right? I feel like if you know stuff, you pass. Right? I get 0 extra money for failing people. They get mad at me when people fail. Right? I have no incentive to fail you. I like all of you. Even the black box people. I like you all. I like you all. I want you all to pass. Right? But I want you to leave this class and know stuff. Right? That's hopefully why you're here, and because your biology advisor told you had to be. But mainly, I hope you want to learn some stuff while you're here. Right? That's what I want. So, in the immortal words of Tom Cruise, help me help you. All right. So, we have to have enantiomers. We have to be able to distinguish enantiomers. So, stereo centers need so you need to be able to name stereo centers so we can distinguish them. The way we name stereo centers is stereo centers can be R or S. Right. R is like revelatory or erectus or something, right? But S I know for sure. S stands for sinister, right? R is in the right-handed direction. That molecule is right-handed. S, that molecule is left-handed. Molecule is not to be trusted. It is sinister. Why? Why is left-handed sinister? Let's go back in time. Middle Ages, right? What's the point of a handshake other than to give someone COVID? But what was the point of the handshake back then, right? It was, I am going to give you, this is my sword hand, this is my stabbing hand. We're going to shake hands. I'm going to give you my dominant hand. So you know I don't have my weapon hand. I'm showing it to you. It's empty. We're all good. But left-handed people were like, hey guys, wink, wink. This is my good stabbing hand. Ah, gotcha. Right? So the reason it's sinister is because left-handed, we got any lefties in here? Okay, everyone's trustworthy. Excellent. Right? So, and the Zoom people can't stab me. So, at least not right now. Right? So, it was that it was, hey, here's my dominant hand, and you tricked them, you can still get it. Right? So we have R and S. Right? Whenever you have a pair of enantiomers, every pair of chiral carbons, I guess, every pair of enantiomers has one R and one S. Right? So if you have, so that those two molecules that I showed you, like the models, one was the R enantiomer and one was the S enantiomer. They always, if you have enantiomers, they always are paired up. One's S, one's R. So how do we assign R and S? Right, we have to assign priority. So we need to assign priority to each group on the chiral carbon, and then we get to play connect the dots. But we have to assign priority first, right? So then that leads to, how do we assign priority, right? How do we give priority to each group? Oops, that's the wrong word. By like all the letters. So the atom with the higher atomic number has higher priority. Right, so we have a chiral carbon like we have been drawing, right, where we have like say fluorine, chlorine, bromine. So we have our chiral carbon, little green dot here, right? And what we're going to do is we're going to look at each atom attached to that carbon, right? So we're going to look at chlorine, fluorine, or sorry, carbon, fluorine, chlorine, and bromine. Right, so we're going to look at that, each atom directly bonded to that carbon, and we're going to figure out which one has the highest atomic number, which one has the lowest atomic number. And by figure out, I mean know, because you all took Gen Chem. So which one of these has the higher atomic number? Bromine has a higher atomic number. Correct. Thank you, Zoom people. Now what's next? Chlorine, then fluorine, then carbon is last. All right, so you need to know which ones have the higher atomic number. I'm going to put this here now. I'm going to go over a slide real quick. Oops. Can't write. All right. I would rather die than give you a periodic table on one of your exams. All right? I'm never going to do that, not in a million years. What you need to know is the following: hydrogen, carbon, oxygen, fluorine, chlorine, bromine, iodide, right? The atomic numbers increase that way and down. That's like, I don't know, 99% of the atoms that I'm ever going to put on a chiral center. Maybe 100% of them, right? I'm not going to like branch out into like phosphorus or sulfur. And I made a solemn promise to the early section I'd never put boron on an exam, on a chiral center. So basically, you need to know these. If you know your atomic numbers increase left to right and then down, you're good, because you passed Gen Chem, right? So I should be able to give you a chiral center, right? So and you should be able to assign the groups on that chiral center, right? So we just look at that first atom, and again, it's going to be bromine, fluorine, carbon, hydrogen. Now, hydrogen is always fourth priority. Hydrogen is just a gimme, right? It's always the smallest atomic number is always number one, right? So easy enough, right? So you always know hydrogen. All right, so when there is a tie, compare the next atoms until the tie is broken. And under this, I kind of have a little sub rule here, which is break your tie as fast as possible. Right. So what this basically means is that I want to, if you could like compare two things and they'd be tied again, or you could compare two different things on the same carbon and break the tie sooner, you do that. We'll do examples because like saying it doesn't really do it justice. So what do I mean by this with ties? So we have our chiral carbon, right? And we want to figure out priority for the groups bonded to that chiral carbon. So the first thing we do is we compare each atom directly bonded to the carbon and figure out which ones have a highest atomic number. So what we're going to do first is we're going to look at oxygen, hydrogen, carbon, and carbon. Of those four atoms, which one has the highest atomic number? Oxygen. Thank you, everyone. So the oxygen will be number one. Which has the lowest atomic number? Hydrogen. So I've already done 1 and 4. But now I have carbon and carbon, right? I have the same atom here and here. So they're tied. So what you do is you then walk out the next atom. So the next atom on the left-hand side is going to be a hydrogen, right? Because where a line ends, it's a CH3. So the next atom there is a hydrogen. So I'm going to compare a hydrogen to this carbon. The carbon has the higher atomic number. So that means this whole chain, this ethyl group, this whole chain here gets to be number 2. And then this side gets to be number 3. So here, there's my chiral carbon. I look at each atom bonded to that first, right? So I'm looking at each one. What has highest priority? Nitrogen, correctamundo. Low priority is hydrogen. Oh wait, are these the same? Add a carbon. Save it. Okay, we added a carbon, we saved it. Right, so now we have 2 carbons, right? So now we have to walk out our chain and figure out if we break our tie, right? So I have carbon and carbon, I'm tied. I go out again. Carbon and carbon, still tied. Carbon and carbon, still tied. Carbon versus, I said it needs extra carbon. Carbon versus hydrogen, carbon wins. So then this whole chain gets to be number 3. Number 2. Number 2. The person in class from West Virginia will be angry at this, but I'm from West Virginia. I can barely count or wear shoes. Like, what do you want from me? What do you want from me? So you're just going to walk out if you have long chains, you're going to walk out your chains until you break your tie. Now, you can shortcut this, right? Right, when you get better at it, or some of you are already doing it in your head. Right? Hydrogen doesn't always have to be your low priority group. It can be anything, right? So you're like, okay, I've got to compare carbon, 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 and bromine. You're like, okay, bromine has the highest atomic number, so it's 1. But I have all these carbons. What you can do is if they're all straight chains, like if they're methyls, ethyls, butyls, propyls, in the wrong order, sorry. But if they're just straight chains, you can just look at them and go, well, whichever one has the longest chain is clearly going to have the highest priority, right? When they're straight. So like here we can just go like 2, 3, 4. Right? Because if you work out all of them, you're going to end up getting exactly this, right? Because the propyl chain is going to run out of carbons before the butyl chain does. The methane runs out of carbons before all of them.
I was asked here, how do you assign priority to 2 carbon chains that are the same length?
If they're the same length, so if the 2 carbon chains are the same length, you have a philosophical question now. Is the same length they are, is the carbon with the OH on it chiral? Anyone? No. Because to be chiral, you have to have 4 different groups attached to your carbon. And so you have a propyl on one side and a propyl on the other. So it's the same group. So you don't have 4 different groups attached. You only have 3, right? You have the OH, the hydrogen, and 2 propyls. So if you have 2 groups that are the same, the carbon's not chiral anymore, and you don't need to worry about assigning R and S. So it is something where, like, if they're both the same, you can't assign priority, right? Because you're going to end up with a tie on those 2 groups, so you don't have like a 2 and a 3. So you can't assign R and S. So if you don't see that, hey, those two groups are the same, when you go to assign priority, you're going to reach a point where you're stuck and you can't assign priority, so you can't assign R and S. So what do I mean when I say if you can break the tie as quickly as possible? Well, let's say we have something that looks like this. All right, we'll worry about this chiral center right now. All right. So again, first thing, look at those atoms bonded directly to the blue chiral carbon. So we're going to have hydrogen here. So I'm comparing oxygen, hydrogen, carbon, and carbon. Right, so this is going to be 1, 4. Right, and now I have two carbons that are tied. So then I go out again, and I have a carbon and a carbon. Now what I can do here is if I kind of hop off the chain in the same direction, right, I can say, you know what, instead of keeping going over, I'm just going to compare this hydrogen to this carbon here, right? So I get to a place that's different, right? And I use that difference to then compare those groups. And then I can say, hey, this group over here, right, it has higher priority because when I compare this hydrogen to this carbon, the carbon wins. So even though the chain on the left is longer, because you have that branch sooner, that branch gives priority to the other side. So this side gets priority because that branch is there. Right? So even though this chain is longer, right? Even though this one is longer, because that branch comes first, as soon as you break your tie, as soon as you find a way to differentiate those two chains, you're done. Like, all right, my work here is done. I have my differences now. I can assign priority. Yes, ma'am. Yeah, so this, by branch, I mean just substituent, right? So this right here, my wedge here, that's just a methyl group. So we feel pretty okay about assigning priority. We will do more examples, don't worry, I'm not just gonna be like, and we're done. Right, but I want to do the last little thing about priority and then like start using it to actually assign R and S. So the last thing is isotopes. So a heavier isotope gets a higher priority. This comes up the most, like almost exclusively in here with deuterium. Right, deuterium is heavy hydrogen. It's hydrogen that has one extra neutron in it. Right, it is the literal smallest change you can make and still be chiral. So if I have this, right, all of those atoms or all of those groups are different because deuterium is different than a hydrogen, right? Even though that difference is just one neutron, it's different. So now when I assign priority, I have my carbons, and again, we can cheat on this one, right? We know that the ethyl chain is higher priority than the methyl chain, right? But now I have deuterium and hydrogen. Hydrogen is always lowest priority. So hydrogen is going to be 4, deuterium is going to be 3, right? So if you have an isotope, that isotope is going to be higher priority, right? They have the same atomic number, but different masses. So when the atomic number is tied in their isotopes, you just go like, hey, which one's heavier? Which one wins in a fight? Deuterium is twice as heavy as hydrogen. I would take it in a fight. Right. So, yes, ma'am.
So it was asked here if you would ever have more than 4 groups or count to more than 4 groups on a chiral center.
You can never count above 4 because carbon can only make 4 bonds, right? So it's the 4 groups coming off of one carbon. So if you count 3, you miss something. If you count 5, too much. You've gone too far. Carbon can only have 4 bonds. This isn't Texas. I know everything's bigger in Texas, but still, even in Texas, carbon makes 4 bonds. All right, only 4 bonds. So you can only ever go up to 4. This is great. If you lost a finger in a farming accident, you can still get to 4. No problem. No problemo. All right. So we know how to assign priority. Let's use this. Let's play connect the dots. All right. So how do we do this? Right. So there's a bunch of different versions of these rules, and we're going to work through all the different versions. We're going to start with the easiest one first. And the easiest version of this rule is if the low priority group the 4 is on a dash, so it's pointed away from you, R is clockwise, and S is counterclockwise. Now your first thought might be, how did clocks get involved with this? Right? So we assign our priority. I'll let you write this and we'll go do an example real quick. As my terrible attempt at it is on a dash. So if it's on, right, you have the wedge in the dash. If the low priority group is on the dashed bond that points away from you, that means that R is clockwise and S is counterclockwise. All right, so let's look at kind of our stock example here. Now, first, if I give you a perspective drawing, if I give you a skeletal structure, right, and it's just this, you know that the bond that's missing, the bond you can't see, has to be the hydrogen, right? So even if I don't draw it, you know that hydrogen is there and it's on a dash, right? So then we can assign priority. Oxygen is 1, hydrogen is 4, this ethyl group is 2, this methyl group is 3, right? Now, we now play connect the dots. You connect group 1 to group 2 to group 3, right? We skip over 4. We're just worried about connecting 1, 2, and 3. So we go 1, 2, 3. We went clockwise to connect our groups 1, 2, 3. And we get this. It's R. So when you connect your groups 1, 2, 3, if you go clockwise to do that, it's R. Now, if you are, I've got 2 things to show you that are tricks if you're not a monster. All right. If you write an R like a normal human being, all right, the first curved line you draw when you draw an R happens to be clockwise. Right? So as long as you're not like some like weird person who like draws their R's from the bottom up or some crap, right? You've got bigger problems than remember R and S if that's what you're doing with your writing, right? This from the guy who it looks like he puts a pencil in his mouth when he writes. So like, whatever, right? So cool. So if you go 1, 2, 3 and it's clockwise, it's R when the low priority group points away from you. The only job of the 4, right? The only job this has is it tells you what set of rules you're using, right? So that group, whether it's on a wedge or a dash, or God forbid on neither, right? That its job is to tell you what set of rules, what you have to do to determine RNS. That's all it's there for. You only care about connecting 1, 2, and 3. So now let's go. That is BR. I am sorry. Right, I give you all this crap about how you write, and then I do that. People in glass houses, or people with bad handwriting shouldn't cast stones. So, what's our highest priority group on our chiral carbon? Bonded directly to the chiral carbon, it's not bromine, right? There's an atom between the bromine and the chiral carbon. So we're looking initially at just the 4 atoms bonded to our blue carbon, right? We're looking at N, carbon, carbon, carbon. Which of those 4 is highest priority? The nitrogen. All right. Now I've got a methyl and ethyl and a group with a bromine on it. So what we're going to do is we're going to work out. So we have carbon, carbon, carbon tied. On the methyl group, the next atom is a hydrogen, right? So now I'm comparing hydrogen, carbon, bromine, right? I've gone out 1 atom on each chain, right? So now bromine has highest priority. So that means this whole group is 2. The ethyl group is 3. The hydrogen is 4. All right, so now we go 1, 2, 3 and connect our dots. Right? We had to go counterclockwise to do that. So that's S. So same thing with the R. We can do the same trick with an S. The first curved line you draw when you write an S, again, preface, if you're not a monster, that first line is counterclockwise. So remembering R and S, you can remember if it's clockwise or counterclockwise by how you draw the letters. So far, so good. Not too difficult. I'll give you the hydrogen there. All right, is that R or is it S? What has highest priority? Chlorine. All right, so chlorine, number 1. We know hydrogen is number 4. So what has higher priority, ethyl or isopropyl? Isopropyl. So we're going to have 2, 3. Now, what this shows you, it doesn't matter if you start at the bottom or the top, right? It doesn't matter where you start, like, drawing, but it just matters if you went in the clockwise direction or the counterclockwise direction. So here, so is that going to be R or S? S. There we go. How many chiral carbons does this have? Lower. 1, right? Because so this carbon is bonded to 4 different things, right? Right, so it's bonded to the OH, it's bonded to the hydrogen, right? This carbon's a CH2, this carbon's just a C, right? So those are all different. You can see that they're all different groups, right? This carbon is bonded to 2 methyl groups, right? So right away you can see there's 2 methyl groups, so that can't be a chiral carbon. So our OH should be 1, our hydrogen should be 4. And then, which one, A or B, has higher priority? A, right? Because when you get to them, you get the 2 carbons, right? And you could immediately just jump off the ring and go like, I'm going to compare this carbon here to this hydrogen. Carbon totally wins. So this carbon A is 2. This is 3. Again, we connect the dots. And what's that one? R, mi poco. There we go. And with that, I think we're done. All right, so these are non-superimposable. Oh no, I'm frozen? Ah, son of a dog bone.